This is a conceptual introduction to linear regression. The target audience is psychology graduate students, but anyone interested in an introduction to applied statistics for data analysis might find it useful. I'm going to show some formulas, but in the spirit of the introductory nature of the exercise, I'm going to simplify the notation at times. I'm also trying to keep this brief, so reach out to me if you want to talk about the details or ask questions. So, a conceptual introduction to linear regression, also known as do you like drawing lines? We're going to draw some lines. Like this one with a positive slope angled upward from left to right, or this one with a negative slope angled downward from left to right. Lines. Real quick, let's make sure we're on the same page about linear equations. You may recall from algebra that a line can be defined by its slope, which direction it's pointing, and its y-intercept, where it hits the y-axis. For example, this line can be defined as y equals 2x plus 1, or y equals 1 plus 2x. It hits the y-axis at 1, when x is 0, y is 1. And then when you follow the line 1 unit to the right, it goes up by 2 units. When x goes up by 1, y goes up by 2. In statistics, we'll usually put the intercept first when we write equations for lines. Intercept plus slope times variable. Part 1 of this conceptual introduction. What is ordinary least squares regression? We're going to start by talking about a standard, very common method to find the slope and intercept of a particular kind of line, a line that fits certain kinds of data well. This standard method is called ordinary least squares. If you have a sample of observations, say 100 of them, and you have two variables, you can plot the observations as points on two axes, a scatter plot. If you choose the values of both variables completely randomly, the points will not show a clear pattern, like on the right. If the variables are associated, for example, if high values on x tend to go along with high values on y, and low values of x go along with low values of y, then the points will show up more in some parts of the plot than others, like shown on the left. There are more points in the upper right and lower left of that plot than in the lower right and upper left, because high values on x do tend to go along with high values on y, and low values on x go along with low values on y. To try to capture this association, we might imagine drawing a line through the points, a line that tracks the typical y value along the range of x values. Here are those lines. On the left, clearly there is a positive association. The slope of the line is positive. As you follow the line to the right, it goes upward. In the plot on the right, there is no relationship. And it would look like this if the values of y were chosen randomly without regard for x. The slope of the line is 0. As you follow the line to the right, it does not go upward or downward, it just stays even. These lines are a great way to summarize a relationship between variables, so a lot of the most frequently used statistics basically boil down to finding lines like this. We can draw a line anywhere we want, though, so how do we know which line actually fits the data? For example, I could just as easily have drawn the green line or the brown line on the left plot, but I'm claiming that the blue line is the right one. How did I know that? How did I find the blue line? And I could just as easily have drawn the green line or the brown line on the right plot, but I'm claiming that the blue line is the right one. So again, how did I find the blue line? I used ordinary least squares regression. Simple linear regression is the easiest way to illustrate ordinary least squares. In simple linear regression, the goal is to build a statistical model in which the theoretical expected value of y for a particular value of x, that is the fitted value of y, is an intercept plus a slope times x, where the intercept and slope have been chosen so that the fitted value of y stays near the middle of the actual empirical values of y. We use b0 to denote the intercept and b1 to denote the slope. The goal of simple linear regression is to find the right b0 and b1. Imagine we're studying the relationship between similarity and liking. We have a data set with 16 participants plotted here, and the participants are thinking about one person that they know, reporting how similar that person is to them and how much they like that person. It appears that more similarity is associated with more liking, but we'd like a formal statistical test of this claim. So we find a straight line that attempts to follow the trajectory of the typical or average degree of liking along the range of possible values of similarity. This line is defined by the regression equation. In this case, the estimated value of liking is 2.1 plus 0.4 times similarity. 2.1 is the intercept, and 0.4 is the slope for similarity. The true value of liking for each participant is 2.1 plus 0.4 times their similarity, plus an error term, a residual specific to that participant, shown here with the letter E. Here's an example of a residual like that. This participant reported their liking somewhat lower than average for people who reported the same degree of similarity. This participant's residual is about -1. And this residual is positive 0.6. The true value for this participant is above the regression line, so their residual is positive. You could draw any line that you want through these points and calculate how far each point would be from that line. To get a sense of how far off they are as a whole, it might make sense to square the residuals and then add them up. Squaring them first means that everything you're adding up is positive. Ordinary least squares regression identifies the line that makes this sum of squared residuals as small as it can possibly be. The blue line shown on the screen is unique. Any other line drawn through this same scatterplot would have larger squared residuals. In other words, this regression line successfully represents the typical values of liking at each value of similarity because it is the unique line that minimizes the sum of squared residuals. It comes as close to all the points as possible under one reasonable definition of close. These values are only typical under the constraint that the line has to be straight. This constraint happens to fit this fake data set quite well, but it might not always be true in the real world. This special line, the one that minimizes the sum of squared residuals, happens to be easy to find too. There's a simple algebraic formula for it, given the x and y values. I'm not going to go into that formula right now, but you can ask me about it if you want. Computers can calculate it very quickly. Because the line is defined by minimizing the sum of squared residuals, we call it ordinary least squares regression, or OLS regression. When there's only one predictor variable, it's also called simple linear regression. Most often, we just call it linear regression or simply regression. The slope, B1, is our estimate of the size of the phenomenon of interest, in this case the association between similarity and liking. For every extra point of similarity a hypothetical person reports, they also tend to report 0.4 points more liking on average. So this is the equation for the regression line. The variable y here is called the response variable, criterion, or dependent variable, among other names. I will tend to call it the response, with the caveat that it's not necessarily responding to anything if we are working with correlational data. The variable x is called the predictor, or independent variable, among other names. I will tend to call it the predictor. When we make an equation like this, we are sort of using the values of the predictor to predict the values of the response, and then seeing how far off we are using the residuals. I want to stress that this equation literally describes the observations. If we fit a regression model on a dataset with a certain number of participants, then participant 7, for example, has a y value, an x value, and a residual. And the observed y value for participant 7 is the intercept plus the slope times the observed x value for participant 7 plus the residual or error for participant 7. In other words, for each unique participant, we can write their unique y value as the regression equation plus the residual. So this was simple linear regression with one predictor. Here's multiple linear regression with two predictors, or three predictors. You can just have a separate slope estimate for each predictor. And there's still a single residual for each participant. The residual is how wrong the whole regression equation is for that participant. The observed value of y is the intercept plus each of the slope terms plus the residual. When you fit a multiple regression model, you're still getting the equation that produces the smallest possible sum of squared residuals. Remember this picture displaying what those residuals are? What if I want to add a second predictor variable? If you want, you can imagine a three-dimensional scatterplot. The regression function with two predictors draws a plane through this scatterplot. Most of the time, it's not worth it to try to visualize the data like this, especially because we're quickly going to move beyond two predictors to three or more. But I'm showing this to illustrate the point that the model represents a linear relationship in multiple dimensions at the same time. a flat surface. In this example, the slope for age would represent the relationship between age and blood pressure at any given weight. The plane is flat. Flat in the same way that the regression line in simple linear regression is straight. So the relationship between age and blood pressure is assumed to be linear and constant regardless of weight, because we have no interaction between age and weight in this model. We will talk about statistical interactions in a couple weeks. So just the way the line slices through the cluster of points on the left as close as possible to each point, on the right, the plane slices through the cluster of points, getting as close as possible to all of them. The result is a set of slopes that allows the fitted values to come as close as possible to the observed values, even though the observed values are scattered all over the place and the fitted values sit on nice straight lines, by choosing slopes that keep the residuals as small as they can be. A quick recap of terminology. What we're talking about today is basically the default kind of regression, so you can just call it regression. Probably the best compromise between specificity and wordiness if you're writing a results section is to call it linear regression. If someone refers to ordinary least squares regression without further clarification, they're also referring to this same thing, but you don't need to call it that in your empirical research reports most of the time.